So then, now that we know what an EA equals R factorization is, we want to turn to the problem of calculating EA equals R factorizations. And the key ingredient into this process is the idea of an elementary matrix. So what is an elementary matrix? An elementary matrix is a matrix that's obtained by performing exactly one elementary row operation on the identity matrix. So let's see an example here. So again, if we want to construct an elementary matrix, what we do is we start with an identity matrix and we do exactly one elementary row operation. So here we have our first example. We're starting with the 4x4 identity matrix here. And we do the row swap where we switch row 1 with row 2. That produces this new matrix. And this new matrix was obtained by doing exactly one elementary row operation on the 4x4 identity matrix. So we call this matrix an elementary matrix. Here's another example. In this example, we're starting with the 2x2 identity matrix, and we are scaling the second row by the number -1/9. So now we produce the same thing as the 2x2 identity, except the second one of the diagonal is now converted to a -1/9. This is another example of an elementary matrix. We took an identity matrix and we did exactly one elementary row operation. Here's another example. Here we're starting with the 3x3 identity matrix, and we're doing the elementary row operation obtained by adding 3 times row 3 to row 1 to get a new elementary matrix. So if you want to define an elementary matrix, take your favoritely sized identity matrix and do one elementary row operation, and the result is called an elementary matrix. Now, what's the point here? Well, let's say that you define an elementary matrix E. So again, you do one elementary row operation on an identity matrix and call the result E. The whole point of this is that if you take that elementary matrix and multiply by any matrix A, the result you get is exactly what you would have gotten if you did that elementary row operation on A itself. So let's see an example here. Here we have an elementary matrix E, and this one's 3x3, and it was obtained by doing the row swap row 1 with row 3 on the 3x3 identity matrix. So now I'm taking this elementary matrix and I'm multiplying by this particular 3x4 matrix A. Well, let's see what I get. What I'm supposed to get when I do the product is whatever the result is when I switch row 1 with row 3 in A. So really, to the right of the equal sign, I don't have the right thing here. I need to swap those two rows. So if you construct an elementary matrix from a particular row operation, you can then use that elementary matrix to multiply by any other matrix on the left, and the result is what you would have gotten if you did that elementary row operation on the particular matrix you multiplied by. Now, I think it's worth making one crucial observation about row operations themselves. One of the reasons that elementary row operations are so useful is that they're reversible. So if you do an elementary row operation and then you regret it later, you can always undo the elementary row operation. For example, let's say that you swap two rows of a matrix. So here you take this 3x4 matrix and then you swap row 1 with row 3. Well, if you regret that decision, you could just take the result and then swap row 1 with row 3 again, and you're back to where you started. So the swap between row I and row J is reversed by the same operation. Just swap row I with row J again, and you're back to where you started. Row scalings are also reversible. Let's say that you do a row scaling where you take row I and you scale by a number C. If you regret that decision, you can undo that operation by taking the new row I and scaling by 1 over C, or the reciprocal of C. Remember that we always require that we use non-zero scalars when we do row scalings, and the reason is precisely because of this. If we scale a row by 0, we just zero out all the data and we lose all information. if I multiply by a number, like in this example where we multiply row 1 by 7 to obtain a new matrix, if I decided that I didn't actually want to do that in the first place, I could reverse this decision by now scaling the new row 1 by 1 over 7. And row addition is also reversible. If I add c times row j to row I, and then want to undo that, I could take the new row I and subtract c times the new row j, which would be the old row j. So I could take, if I add c times row j to row I could reverse that decision by subtracting c times row j from the new row I. So here we have an example of a 3 by 3 matrix, and we perform the operation row 2 plus 5 row 3 goes to row 2, so that changes the second row. But let's say now I regret that decision. What I can do is I can take the new row 2 and subtract 5 times row 3 from it, and I get back to the original matrix. So the punchline here is that you can always reverse an elementary row operation. And one way to think of this is that elementary row operations are invertible. And this has consequences from the perspective of elementary matrices. What this is saying is that if you construct an elementary matrix by doing one row operation, you can invert that elementary matrix by constructing an elementary matrix corresponding to the reverse elementary row operation. So we just said that you can undo a row swap by doing the same row swap. What that's saying is that the inverse of an elementary matrix corresponding to a row swap is just an elementary matrix corresponding to the same row swap. So here we're looking at an elementary matrix obtained by switching row 2 with row 3 in the 4 by 4 identity matrix. What our theory is saying is that this matrix is invertible, and its inverse is given by switching row 2 with row 3 in the identity matrix. Remember that the inverse operation of scaling a row by a number c is scaling that row by 1 over c. So this says that if you want to invert an elementary matrix that corresponds to row scaling, you do the same row scaling, except instead of using c, you use 1 over c. So here we have a 3 by 3 example where the elementary matrix we've constructed corresponded to scaling row 3 by -8. Well, the reverse of that row operation is scaling row 3 by -1 over 8. So the inverse of our elementary matrix here is the elementary matrix constructed by scaling row 3 by -1 over 8 instead of -8. Finally, row addition is reversed by row subtraction. So if we want to reverse row I plus c times row j goes to row I, we use row I minus c times row j goes to row I. So in this example here, we're starting with the elementary matrix that's 3 by 3, obtained by adding 4 times row 2 to row 3. This matrix is invertible, and to find the inverse, all we need to do is construct the elementary matrix obtained by taking row 3 and subtracting 4 times row 2. So we can always invert elementary matrices, and the effort is minimal.